So for part E, we want to find out what the rate of gasoline consumption is driving down the highway at constant speed. Now we can use our mileage is equal to 30 miles to the gallon, because this was measured under highway conditions. And so we can say our rate of consumption is just 60 miles an hour divided by that 30 miles per gallon. Not too difficult math, we end up with 2 gallons per hour. Okay, and if gasoline is 3 kilograms per gallon, this is about 6 kilograms per hour. But we can also take this and multiply it by the 125 megajoules per gallon of gas, and also divide by the 3,600 seconds per hour. And what does that give us? Well, the gallons cancel, the hours cancel, and we have megajoules per second, or megawatts. And this corresponds to 70 kilowatts of power. That's the rate at which we're using gasoline. And so this would be the power in. It's the rate at which we put energy into our car. And so the power out that we get is just the power in times the efficiency of 12%, which is about 8 kilowatts. So this is the power that the engine is putting out in order to maintain your constant speed on the highway. Much, much less than the 170 kilowatts that the engine is capable of putting out. So let's go back a moment. We'll just remember that number and take a look at the rate of carbon dioxide used. Because the rate of carbon dioxide use is the rate at which you use gasoline times this 44 over 14, because 44 grams is the mass of a CO2 atom or a molecule, and 14 grams is the mass of a methyl group. But you also want to multiply by the 1.4. I'm saying that I use the gasoline that results from the tar sands in Alberta. It's a very energy-intensive extraction and refining process, so we have to multiply by 1.4, and it turns out that I'm producing carbon dioxide at a rate of about 26 kilograms per hour as I drive down the street. Lastly, let's take this 8 kilowatts and use it to calculate the force on the car. Because again, when we look at the car driving along at constant speed, the force of the engine must equal all of this resistance force, because the acceleration is equal to 0. And we know the power, and we know that power is equal to velocity times force. Force times velocity. And so the force is going to equal power divided by the velocity. And the power is about 8 kilowatts. This is the power that the engine is delivering to the wheels, divided by the velocity, which is about 27 meters per second, yields a force of about 300 newtons. So this is a force that the engine has to put out to compensate for the air resistance and the rolling resistance of the tires. The rolling resistance of the tires is usually less than the air resistance, so we might say that the air resistance is about 200 newtons. Right? Well, that's the force of gravity on about 20 kg. Right? And 20 kg is about 44 pounds. So the air resistance of the car driving along is about 44 pounds, which, I mean, to me makes reasonable sense when I think if I put my hand out the window. Be careful if you do that. I'm feeling a resistance of maybe 1 pound. The whole car, 44 pounds, I can believe that.